Okay, welcome back, everyone. Today we're joined by Professor Josep Cornella, who is now leading the Sustainable Catalysis Laboratory at the Max Planck Institute for Kohlenforschung over there in Mülheim, Unterwehr, Germany. So it's fantastic having him here today.
Thanks.
I got to be honest, the Max Planck Institute is definitely one of the institutions I want to go see and just go. I mean, the chemistry that goes on over there is absolutely stellar. I mean, obviously yourself, but Professor Benjamin List. Personally, one of my favorites, Professor Alois Furchner. I really like his chemistry with alkymetathesis, iron chemistry, total synthesis. I mean, it's all it's the Max Planck Institute is super fascinating chemistry. So
yeah, it's great to have these colleagues around. Yeah,
right, to be able to just go. I mean, I'm sure the seminars are great. To be able to just, I mean, if you're unsure about something, especially for the students, if you're unsure about something, to have those people there to just run some ideas off of is, I mean, absolutely awesome.
Yeah.
Plus, Western Germany, beautiful cities over there. So I know we were talking, Dortmund's not too far. I'm a big Borussia Dortmund fan, so.
Okay.
In any case,
here people is divided between Dortmund and Schalke.
I was say there's a huge. I mean, obviously people know that they're Klassiker, which is Bayern and Dortmund, but people are unfamiliar with the Schalke Dortmund rivalry. That's a huge rivalry.
Yeah.
But before we get to to your chemistry, definitely want to start with your background a little bit. Pardon my Spanish. I don't really know any Spanish, but I know you kind of grew up in the northeast part of Spain, La Bisbal del Penedès.
That's the hometown. Yeah, that's right.
That's not
good
too
pronunciation.
Appreciate it. It's the only Spanish I know is really watching La Liga soccer, or Liga football. So it's about the only Spanish I get. But it's not too far from Barcelona. I mean, several miles out, but that's probably the closest thing to there. But you are the coast, but South Catalunya. I don't know if you want to tell us a little bit about kind of growing up. I don't know if you were born there and grew up somewhere else, but I don't know if you want to tell us a little about the small town there. But
yeah, so I was born, as you said, in this town called La Bisbal del Penedès, and this is northeast of Spain, in Catalonia region. It's a very tiny town. I think we are 800, and then with the whole, let's say, small county, maybe 2,000 or 3,000. All my friends still, they are spread around the world, but this seems to be like the connection point that we go every year, and we all meet there, so it's great. The closest one I had to study was Barcelona, so I went for chemistry there, and that is not far; it's about an hour or so.
Yeah.
And I lived in Barcelona for a while. It was kind of a little bit unfeasible for me to go back and forth. So I just stayed there. Which for Americans, I guess, it's just a common thing. You just leave out for college, right? So this was cool, and then that opened a whole world, as you can see, right? Going from this small village to live in a city like Barcelona, that was came with a lot of opportunities and new friendships and new ways of seeing life, I guess. Yep.
Yeah. Barcelona is. I mean, I'm going to make so many football references today because that's just kind of the only thing I really grasp on. But Barcelona is an absolutely fantastic city. I'm not really as familiar with the STEM there. So University of Barcelona, I'm not actually familiar with, the education system. Before touching on that though, was STEM in general something that was kind of something you'd study through a young age, leading into Barcelona, or how did that kind of all transpire?
What was the question again? Sorry.
So before attending University of Barcelona, I don't know if you had studied chemistry at all, but I'm saying through a young age, was STEM kind of something you've always been passionate about?
Yeah, it was basically the subjects at the school that I was more good at, or it was easier for me to grasp and apply. So I had a very cool chemistry teacher at, I guess when I was between 15, 16, right before my bachelor studies. And yeah, he really influenced me. And he said that chemist was probably like one of these areas that connects all the sciences somehow. And it turned out to be true. I still to this day, I think chemistry is like, as the slogan of ACS Central Science, right? That is central to everything, all the sciences. But it's a little, I mean, it's true. And if you learn chemistry and you understand chemistry, in our case, organic synthesis, you can jump into a lot of areas and really understand them. So that was kind of my first sort of motivation, was this teacher. So how important it is sometimes, right, to have a teacher that at the early stage tells you something, and that, somehow you just follow that path, and yeah, I liked it, and I continued doing so.
Yeah. More often than not, I find that, people I talk to, it's like nine times out of 10, if you have a very passionate teacher, like, that kind of puts you down this path, I think.
That's right.
And that's true almost everywhere. What was it kind of like, when you moved to Barcelona? Because I know when at least people that I've spoken to who kind of grow up, let's say, I don't know, kind of farmlands, but like not really near any big cities, leaving to go to a big city and attend university. Did your parents encourage you to go do this, or was this kind of was it an easy decision? Or
so if you wanted to study, you had to go somewhere and outside of this small town. So Barcelona seemed like a good option. And there was also a place where I could stay, and I didn't share a flat. I went to a student's residence, that you would say. And there is basically like a place where a lot of students from different disciplines stay there, and everyone is studying at the same time or partying at the same time, and then you make a lot of connections from different places, right? Engineering and pharmacy and biology and architects, and everyone is under the same roof. And that was like an incredible experience for 3 years for me. It was very enriching. And it got me in touch with a lot of people from different places, from Spain and the rest of Spain, right? From different parts of Spain, or some foreigners, but that was great. That was a great time.
Yeah. So I know ICIQ is there, which is a top university in Spain. What I'm curious is how, did you go into University of Barcelona as a chemistry undergrad, or because I also know you did like undergraduate research, studying like allylboron chemistry.
That's
so
right.
How did that kind of opportunity arise? Like, how did that come about?
So that was an opportunity that presented to me when I was in fourth year of undergrad, and there was it was called so in Spanish it's beca de colaboración, which means basically collaboration fellowship or something. It was for 3 months in summertime, or even 2 months, not that much. And you're just in fourth year, so you're already a little bit aware of what you like. So you know what you like, what you don't like. So I liked organic synthesis, so I just checked the groups there, and I said, there is this fellowship, would you mind? I checked one of the groups. The PIs were really cool, and they said, yeah, just come join our lab for 2 months. And then I stayed for the master's the subsequent year. So I liked it so much. The environment was so cool, and the chemistry was very nice. And I just joined the master's program afterwards.
Yeah. So and then after that, you attended to, you decided to go do your PhD. Was that an easy decision? Was that kind of a natural progression, or was that?
The PhD was something that I really wanted to do, to be honest. During the master's, I already said, all right, this is cool, and I can see myself doing this. It was a strange feeling because you finish the undergrad or the master's, and then you think, okay, that cannot be it, right? There had to be something else. And that was the PhD, the obvious extension, right? I could have gone to work and do exciting stuff for sure, but I wanted to keep doing this research. And then the opportunities, so that was 2008, right? Where the recession hit, and there were like a lot of cuts, right? In funding, in opportunities, in fellowships, in everything. And so I was basically in that period where there was no fellowships for people that were like in the 6th, 7th position in the ranking of the university. I was not the best in my class by far. So they didn't give me any fellowship, right? So I said, all right, if you want to do the PhD, at what cost do you want to do it? And then I just packed my bag and I went to the UK. There was this opportunity that it was a former student of the University of Barcelona, Professor Igor Larrosa, that he was at Queen Mary University, and he said, I have an opening and just come interview, right? So I went there. I barely spoke English. My English is not fantastic, but that English was horrible when I arrived there. And he said, all right, he actually gave me the opportunity, right? He said, like, all right, you understand chemistry. The English will come with time. Don't worry about it. We will speak always in English. And to this day, we still speak in English to each other, even though we are both from Spain.
Spain.
We speak Spanish, right? It's quite funny. Yeah.
Yeah, that's really interesting because I know Professor Igor Larrosa is now at University of Manchester.
That's right. It was before the move, right? I was the first PhD student of his lab, and we set it up, everything, and it was the beginning of his career. It was very exciting. Also.
So how did that kind of opportunity arise? So like, did you? I mean, I guess you had the Spain connection, but were you like, how did you, like, I mean, did someone tell you, hey, Professor Larrosa's at?
That's right. That's
Queen
basically
Mary?
what happened. Mm-hmm. At a Christmas party. Or some sort of party, I don't remember which one. One of the professors of the former PhD advisor of this guy, of Igor, said, one of my former students started his own lab in London. Why don't you check it out? And that was basically the Spanish connection, but it could have been like just a normal network without nationalities, right? It could have been a former student of mine, right? So that's how it came about.
From one big city to the next, how did it? Because I mean, like you mentioned, you spoke broken English. So how was the change from Barcelona to London? I'm sure I'm sure like maybe architecturally they're super different as well, but I don't know if lifestyle, like how was the lifestyle change? Like what kind of stuck out when you made that move?
I didn't know anything about the English sort of way of living or culture. I mean, not nothing, but I never visited the UK before. Sure. So it was for the interview already the first time. And it was shocking, right? I mean, London is gigantic. It's endless. The people is very different. But it was very cool in a sense. I don't know. At the end, so when I finished my PhD, I was very sad to leave London, to be honest. But it was very challenging at the beginning. I didn't have a house. I didn't speak English, so I didn't know how to look for a flat. Everything was kind of messy. The university was okay, helping in the sense. I apologize for this, but this is true. It was challenging. So I slept in a sofa for 3 months of a friend of a friend of a friend, and that was the Spanish connection. And then, an opportunity in a flat came up that was affordable, because you can imagine a PhD salary in London. It was pretty challenging to leave and find something that is suitable.
Right.
And that was it. I went for this room, and we shared it with 3 people, and it was great. It was close to the university in East London.
Yeah, that's incredible. That's incredible you shared that, because, I mean, like to just get up and leave, have really nowhere to live, but pursuing that, I mean, in some sense, the dream of just like pursuing the chemistry. I mean, that's super.
I don't know. I had the feeling that I had to do it for some reason. I wanted to do it. The opportunity was there. I always said I was not very good at English during all my years, and I said this is like, we can kill 2 birds with one shot, right? I just go there and I learn English and I get my PhD, so that's pretty good. So that's opportunities that they're not very common, because PhDs usually they will ask you for a level of English at the entrance, right, and so on and so forth. And I didn't have that, so that was cool. Looking back, that was cool, and I thank Igor for that, because he's the one that really, gave me the chance. So.
Yeah. That's super. It's definitely super challenging, but super unique. I'm sure it gave you really unique perspectives, and certainly not ones that a lot of people probably don't have. I mean, I don't know. I mean, students. I mean, especially during the 2008 recession, money was tight everywhere. Sure. Yeah. Basically non-existent in America. So I don't even want to know the fellowships that were available in America. So. Yes, thank you for sharing that. It's definitely.
The English was always that I wanted to learn, and this was the idea, right? So if you go to England, you're going to learn English, which is the language of the science and the chemistry that I'm doing all the time. So And it's not because we didn't. I mean, my parents paid me extra classes of English, but it never got, it never stuck. So they paid me a lot of before, right, during my youth, but I was horrible at speaking and everything. So that was the opportunity. I was gonna say, let's do it.
I was gonna say, growing up kind of in a small town, you probably don't need to speak English because everyone speaks Spanish.
No. And even in my region, I didn't even have to speak Spanish, right? I learned how to speak because my mother language is Catalan, right? So we were speaking Catalan with all my friends. We speak in Catalan. My family, my wife, the family of my wife, we all speak in Catalan. So Spanish, I started to practice. You hear it in the TV, and there's people that speak it in the street and so on. But my closest friends or my closest circle would never speak Spanish. So I learned to speak Spanish when I was like slightly older, because I spoke very bad Spanish.
Wow!
But now it's smarting out.
That's really interesting. I didn't even know there's two different languages in Spain. That's super fascinating. Okay, so Catalan's a different language.
4 official ones. So, but yeah.
Oh wow. Okay, that's really fascinating. And they're not even close to one another. Like you couldn't even.
Well, there are some that are close that come from Latin origin and so on. But then there is one that is very, very strange and unique, which is the Basque, that is spoken in the north of Spain, or a region that is called the Basque Country. And this language, I don't want to say things that I don't know here, but I think like the origins are a little bit unknown where it comes from, because it's so different from all the even European languages. So I don't want to say where it comes from, but it's very strange, and I cannot understand anything from that language.
That's interesting. But like, so someone who doesn't know, again, I don't know any Spanish. So like, if someone spoke to me in Catalan and Spanish, like, could I tell that there's a difference? Like, is it that obvious, or is it like?
For somebody, I've never been in this situation, right? It's not that different. Fair. You would say so. This Catalonia region is between Spain and France, right? Is in the area that joins the peninsula, right, where Spain is with Europe, right? And in that region, there is where Catalan is spoken, and it basically has the influences of both, of French and Spanish. So Spanish people really understand, I think, no problem after a while listening. I know a lot of Italian people that come to live in Spain, in Barcelona or in Catalonia, and they just pick it up very easily. So it's not that difficult if you have the Latin basis as your mother language. Okay. Right? If you're German or if you're English, probably it's a little bit more complicated because of the structure and so on. But I think it's as difficult as for me to learn Italian or Portuguese or something like that.
Interesting.
No, it's not complicated. But for you, I don't know if it sounds very different.
I know very, I know like basic German, so I know like Germanic, but I mean, I don't know a lick of Spanish, so. But so you're at it's Queen Marie University of London. I think it's the full name. It's out in London. Queen Mary University of London. And you were working on, your Professor Igor Larrosa's group, and you're doing, you're kind of using aromatic carboxylic acids to do metal-catalyzed decarboxylative reactions. You want to tell us a little bit about your graduate work and, how that came about?
Yeah, so when I joined, Igor wanted to do this coupling, which was a combination of a CH. So he wanted to basically replace the common transition metal catalyzed cross coupling, like the Suzuki or the Negishi and so on, that we have an organometallic nucleophile and an aryl halide or something halide or pseudo halide as electrophile, right? And his idea was, why don't we just start from a CH bond in the place of the nucleophile, and then in the place of a halide, we'll put a carboxylic acid, that there are plenty, right? And but this is an oxidative coupling, basically. These are two sort of nucleophiles, and we need an additional oxidant. And starting to look at these combinations, we developed a method. It was quite restricted to in terms of compounds and so on, but we learned a lot during the development of that. And we realized that actually transition metals were good at transition metals that were not known to do the carboxylations. were actually suitable for it, like silver and palladium, and we've done some gold decarboxylations and so on. So that was basically, I spent a lot of, so all my graduate program, all my graduate studies removing CO2 and blowing it to the atmosphere, which is not great from the selling point, but obviously it was good because you would take basically carboxylic acids that are super cheap, stable, and pretty much everywhere in every sort of regiochemical setup and stereochemistry, and you can just basically use them as electrophiles. That was the idea, or nucleophiles, aryl donors in synthesis, which I think is the title of my thesis actually.
Yeah. I mean, you guys are definitely onto something there, because decarboxylative coupling is now, really hot right now.
And we were focused on aromatic.
Right.
That's
fair.
And that was kind of the so the aromatic carboxylic acids were, the carbon sp2 was our obsession back then, and the aromatic and the carbon sp3, there was not a rush for need. There was no this escape from flatland sort of current movement that we have right now, from influence by the medicinal chemists that are asking for new and much more 3D molecules, right? So we were basically trying to mimic the biaryl sort of cross-coupling, canonical cross-coupling. Yeah.
Right. Yeah.
Yeah.
Yeah. Escaping flatland is I always love to hear that. It's very admirable to go try and escape it, but the biaryl coupling is just the easiest thing in the world. So it's like, you know what, we're gonna do it. It's a very admirable goal.
But nowadays the opportunities are amazing, right? For
right. It is.
SP3, it's just exploded, and by discovering new modes. But we can talk about it later if you want.
Yeah. So, after your PhD though, you went on to go do a postdoc. Your first one with Professor Ruben Martin at ICIQ.
Right.
Was a postdoc. I know you mentioned earlier you thought about becoming a teacher, but postdocs are a first step to becoming a professor. So, was this definitely a natural progression, or what was kind of the thought process for a postdoc?
I wanted to continue, to the academic pathway, and I identified Ruben as a way to go back as well. I was like 4 years in England, 3.5, 4 years. That was enough. So I decided to go back for a while. I opted to one of these good fellowships from Europe, which is the Marie Curie Fellowship, that basically allows people to move intra countries within the European Union. Also, there are fellowships to go to the US or outside Europe, like Japan or US, but they are much more. There are less of them. So I got one of those, and I went to Ruben. So he came for a talk at Queen Mary, and we were chatting, and he said, "Why don't you come? I have money to cover for the first months, and then if you get the fellowship, then which I think you have chances to do, then we basically." We're in business, and that's what happened. So we got the fellowship, and in there, it was ICIQ. It was a great place to do chemistry and catalysis. It was like one of the reference places. So it was the Tarragona is very close to where I was born. It's also in the Catalonia region, in the north of Spain. So it was kind of going back home, and I said yes very quickly, and. So I went there, and I was exposed there to completely different chemistry, which is the nickel chemistry. I really delved into that, and that was an incredible world that I didn't know at all. Okay, so I had to really read and experimentally nickel chemistry, organometallic nickel chemistry can be very challenging. So I was exposed to all that, and in there, funny enough, the projects and the programs that I was working on were to carboxylate now organic molecules. So to put CO2 back in to organic framework. So it was kind of a trade-off for what I've done in England, and then to pay back somehow.
Right.
And I developed all these catalyzed carboxylations and with Ruben. Yeah.
Well, carboxylative, carbon dioxide insertion reaction to sound great for funding and grants. I'll just, it sounds great. We'll take CO2 out of the atmosphere and we'll start inserting it in the molecule. It sounds fantastic. but quite
Right,
difficult. I mean,
yeah.
like you mentioned, I mean, nickel organometallic chemistry can be quite difficult, but we'll come back to this a little bit later because I know, you guys were some of the pioneers for making nickel zero air stable pre-catalyst, which is super cool. But you were doing kind of CO bond activation. What, what? I guess maybe we could talk about this now. What kind of makes nickel chemistry so difficult? Like nickel organometallic chemistry, like what makes it so difficult to do for people that are really kind of unaware of this field?
So nickel is in the same group as palladium, right? It's just above palladium, but its reactivity and stability of organometallic compounds is very difficult and it's very different. Sorry. So organopalladium complexes. So analyzing, let's say, to get insights into mechanistic details of an organometallic palladium catalyzed reaction, it's slightly easier due to the stability of these organic compounds, right? They're stable, they're diamagnetic, you can NMR them, right? You can crystallize it nicely and see what you get. With the nickel, you have a lot of peculiarities, and all boils down to one problem, and it's the ability, the ability that they have to change oxidation state by one electron. So basically you get all these single electron transfer processes that basically make nickel carbon bonds weak, and then you start generating carbon radicals or X radicals. Whatever is bound to nickel can easily homolyze sometimes. They are sensitive to all these stimuli, right? With light, probably you homolyze the bonds. They are sensitive to air, obviously. Some palladium complexes are not sensitive to air, less sensitive. The nickel 0 is extremely sensitive. The nickel 1 is also very sensitive. The nickel 3 is very sensitive, and the nickel 2 depends on which one. So it's a tricky business to work with nickel. And then you have all these redox events within the same complex. That when you have one isolated complex, it seems that it's there, and then all of a sudden, if it's a nickel 1, then it turns into a nickel 2 and a nickel 0. So it disproportionates, and then everything goes to so it goes in different directions. And the opposite, right? You have a nickel 3, nickel 1 gives you nickel 2. So there is a lot of funny things that are very dependent on the ligands and what do you put into that metal center. And that I realized early on that this is going to be not easy. But I worked at the beginning with this diamagnetic compound, so I was fine. But then as soon as I started in the carboxylations, I started into the single electron transfers, and that was much more challenging. But that gave me the knowledge to actually go to the Baran lab and do the decarboxylative redox-active ester. Right?
Yeah. So I was going to say your next postdoc journey, let's say, was with Professor Phil Baran at Scripps. What kind of drew you there to go to Scripps to do the chemistry there? Like what was as you mentioned, it's kind of decarboxylative more chemistry, but what drew you to go to leave and go to America?
Yeah, so America was something that I really wanted to do for a long time. I thought that going into exposing myself to that type of environment, I thought that it would be like the best. Some of the best groups are in America. I already had experience in a couple of countries in Europe, so I thought my next step, I think it would be cool if I now check, right? I feel ready in terms of training that I can go there, do something. So we went together with my wife that is also a chemist. So she joined the group of Shenby, Ryan Shenby, Scripps, and I joined the group of Phil. Yeah. So we were both there at Scripps at the same time, and obviously what drew me to Baran is needless to say. I mean, I've been following his chemistry for a long time. I thought that all these. So by the time I was in my first postdoc, or at the beginning of my first postdoc, he started doing some metal-catalyzed radical chemistry with iron. And then I said, okay, this I think is an area, not total synthesis, but is an area that maybe I can come and bring something, right, to do something there. I knew that they were not like by training organometallic people, right? They were like organic synthesis focused, and I wanted to get that sort of application-driven mentality of like, okay, this is a fundamental, but what is the bigger picture here? What is the organic synthesis that we can use, to apply all these methods that we're doing? And that was something that really attracted me from that lab.
Yeah, because I recently, like the chemistry coming out of other groups, is doubly decarboxylative cross coupling, using electrochemistry and nickel, but you have to use. Well, I say it's like it's a bad thing. It's not, but you have to use a redox-active ester. So you have to put on, a phthalate in order to do the chemistry. But did that come out of work that you had done? Because the kind of the early concepts of redox-active esters to do this kind of chemistry, is that kind of where you started it?
Yeah. So okay. So the redox esters was something that kind of naturally evolved from. So when I joined there, they were doing these Minsky sort of radical additions of sulfinates, right? The diversinates that people love in medchem. And one of the main, they had a problem in one particular sort of in the industry. They had a problem in one particular sulfinate, and I remember talking to one of the grad students that was there at the time, Ryan Giannatasio, and we were talking and we were saying that it would be great. The Barton ester, if you decarboxylate, right? If you generate a Barton ester and you shine light, you should generate this tertiary radical. That was the one that we wanted to do for another purpose. And then when we went to Home Depot, we bought this lamp, like 3 watt, 100 watt or whatever, and we just prepared the redox ester. And the idea was maybe what we can do is we didn't call it redox ester back then. Okay, we just called it the Barton ester, right? Which is with this thiopyridone, right? And then we basically irradiated that, and I had the expertise of a nickel 2, and I knew that radicals would get trapped by aryl nickel complexes, and they would probably snapshot and form a carbon-carbon bond. So I prepared the nickel aryl on one side, and he gave me some of the Barton ester that he had been working on the thesis, and we just shine light into that mixture, and in the GC mass we saw the little peak of the carbon-carbon bond. It was like awesome, right? I mean, great. But then, the issue was how we turn this into something useful, because Barton esters are very light sensitive, as you know, and so on. And so back then, what we thought is that the light is necessary to homolyze all this, and then the radicals get trapped by the nickel. So testing, more people join into this sort of adventure. Phil was very excited about the prospects of it, and eventually we realized that we didn't need the light. We could turn it catalytic. And the simple idea is that basically because of these things that make nickel so complex to study, which are single electron transfer events, because thanks to this, the nickel is able to pump an electron into some sort of redox-active ester, which was what we called these hydroxyphthalamides, generate the radical anion, kick out the phthalamide and generate a carboxyl radical, decarboxylate, and then that radical then gets trapped by the nickel, and that can go. And that was the first publication that happened with organozincs, and then the alkyl zincs was another article, and then the boronic acid. So we were able to rapidly, because a lot of people joined in that adventure. It was like a lot of fun with a lot of people in the lab. Actually, yeah, it was good.
That's awesome. So just on
it was really
switch over to. Definitely want to switch over to the research you're doing now at the Max Planck Institute, but I'm kind of curious to see, your first impressions when you moved over to California, when you first moved here, over in, I think it's in San Diego or La Jolla. I don't actually, I forget what city it's in.
Yeah, it was in La Jolla, yeah. When I moved to La Jolla, for me, it was dream, right? It was a dream. It was like the movies. Yeah. It was fantastic, right? Me and my wife unfortunately, so we were postdocs and we were very dedicated. So we spent a lot of time working in the lab, quite hard, and we were very tired. I remember being very tired during that period of my life, because when we're not working, we're trying to enjoy life, like to enjoy everything as much as possible, right? So we were visiting here and there and so on. So then back to the lab real quick and it was like a nonstop. Like we knew that it was a short period of time that we would be there, so we wanted to do everything. And yeah, it was
That's
it was
awesome.
exhausting, but it was a lot of fun. It was a lot of fun. Yeah.
Yeah, that's incredible. But
Yeah.
following your second postdoc, that's kind of when you moved back to, well, back to Europe, I should say, but over to the Max Planck
Yeah.
Institute. And like I said,
Mhm.
like I mentioned before, now you're one of the group leaders in Sustainable Catalysis Laboratory, and definitely excited to talk about your research now. You're kind of in really kind of multiple areas. I mean, recently I know you're kind of doing a lot of bismuth chemistry, catalysis, but also nickel zero catalysts, but also doing pyridinium salts, I think what they're called, to do various transformations. So perhaps we could talk about each section of research. I guess starting with the nickel chemistry, because it's kind of, I guess, kind of the natural progression. I want to get this right. You're, I don't know if it was you yourself or your group who were able to synthesize those air stable nickel zero still being catalysts, right? Was that okay? I just want to make sure. I thought it was. I just wanted to double check.
Yeah.
But
Yeah.
synthesizing
So,
a nickel
mhm.
zero still being pre-catalyst. I mean, how did you? I mean, like, I don't know, come up with this,
Mhm.
or how did you come across this, or
Yeah.
what?
So the
What's
institute,
the
when I
story
wanted,
behind it?
yeah, so we were working in a completely different area. We were not interested in this, but the idea of having an air stable nickel zero had stuck with me for a long time. Okay. And I remember I had a grad student, first year or second year, well, one of my first crop of PhD students, Lucas, whom I shared this sort of, like, it would be great. I mean, the nickel zero precursors are nickel cod, and pretty much that's it. And it's glove box material. So we were always talking about this. And for a project that he was working on, formal nickel minus two highly reduced nickel species, we're looking at the mechanism. We published a paper, and we were excited about that. But when we looked at the mechanism, we had to prepare 16 electron nickel polythene complexes, right? Which were originally reported here in the institute. This institute is the one that discovered nickel COD, right? So it was kind of the best place. Even
Mm.
the technicians around were, familiar with the techniques. We had the old chemicals like triethyl aluminum, neat, which is not, it's hard to get right now. But anyway, so we had all these at hand, and then Lucas was super skilled, and we started preparing these nickel 16 electron complexes like nickel CDT, CCCs, the trans, the nickel norbornene. And then at some point, he changed these olefins to stilbene because Gunther Wilke, which is a former director of, was a former director of our institute, also prepared it. And it was actually included in the patent of the nickel cod. The nickel just treats
Mm.
a stilbene. However, this is so the funny thing was when Lucas just came to my office with a vial with a red solid, and he opened it, and I said, what is this? And he said, this is nickel zero. And I said, there is no way, right? I mean, there is no way this is nickel zero. He said, yeah, it's a nickel trisostilbene complex. And I said, and then all of a sudden an email pops up into my inbox, and it's his email that took a while to arrive because it was heavy with a CIF structure and the CIF, the crystal structure. And I see it, and it's like, this is amazing. It's beautiful. It's great. And then we started
Wow.
talking and looking at this. And then by investigating a bit more, I think the CF3, we started putting CF3s and modifying it and to turn it even more robust and more better properties and so on. But originally, just the plain stilbene was reported by Wilke in 19th. But I don't know if he realized or not that was air stable, and he decided to go with nickel cod, which is great. Nickel cod is an amazing nickel zero
Right.
precursor, and it's basically the go-to source still nowadays. But yeah, we saw that, and it was like, all right, this is game on. Let's take it, because people, one of the hurdles when you
Yes.
talk to industry people is
Just for
that they don't want to go to the glove box. Yeah.
right. Yep. Just briefly on that, maybe to explain a little bit is why nickel zero is so hard to make, or at least why it's so air unstable.
Well, it
I guess
gets,
why are most nickel zero
yeah. I
complexes?
mean, it's full of nitrogen, right? It's and it just gets oxidized very easily. Um,
Hmm.
So nickel cod gets decomposed is even thermally unstable. So if you have to keep it cold, otherwise these
Hmm.
ligands are so labile that they just fall off. and the nickel aggregates, and you generate nickel black. And the nickel black is inactive. When you have a lot of nickel, it just aggregates and it becomes inactive. So nickel cut was basically the only nickel zero source, but there were beautiful methodologies catalyzed by nickel zero, right? That people could have used, and there were alternatives to nickel zero. A lot of alternatives. There was like wax capsules, there was nickel 2 precursors, and so on. But truly aerostable nickel zeros were not sort of available or like widely applied or studied. And we just decided, with this mentality of an industry that I had coming from the Baran lab, like industry people want simple things. I just thought that it would be a good idea to develop this aerostable nickel pre-catalyst. Yeah.
Right. I mean, yeah. What do you like? What kind of protects the nickel center from, like, say, getting oxidized? Like, what kind of, is it just the packing of the ligands? Like, what kind of, I don't know if you've kind of investigated reasons, if there's multiple reasons why it's not easy to oxidize, or.
We are still looking at why so, really, to be honest with you. And we really think that the stability comes from two factors: the ability to displace the ligand and the capping of the para substituents that protect the top and the bottom. So we've done studies on this, and it seems that it's a mixture of both, but the capping seems to be the most important one. So once we put the terbutiols, now that is our best performing catalyst, the most robust, the one that survives heating and so on. And we are still thinking on why is so, that is so robust. And we're starting to think that these terbutiols might have some sort of dispersion forces that attract each other, right? Like hydrophobic interactions that keep everything into place. And this has been described before. And that is our current thinking of why the terbutyl is so good compared to the CF3 or other ones. But yeah, this takes time, and we're still working on it and trying to find out better, generation and so on.
Yeah. So one of your recent publications, kind of using these catalysts, are taking oxazoles and turn them into azoles.
Yeah.
How does this kind of transformation work then? I don't know if you guys have a good sense of what's happening there.
Transformation that one of the PhD students found long ago, and we thought that it would be cool. I mean, the NO bond is sort of labile, weak, not labile. All right, and if you have a strong, low valent metal like a nickel zero, you can probably cleave that off, and then you turn it into an imine and a ketone. And if you have hydrazine, then you can condense into the ketone and then close back and kick out ammonia. So basically, you can turn isoxazoles into pyrazoles, right? And that, I think, is a valuable reaction, and not for process, because you would probably prepare it's the same precursor. It's a 1,3 keto sort of a synthon that you need for both. So that it's not for a process sort of focus. But in medchem, if you have a structure that has an isoxazole that is very complex, and you just want to see whether that turns, what happens if I change that oxygen for a nitrogen, right? It's like these modern sort of strategies like skeletal editing, or I don't know, that are appearing from Mark Levin and Richmond Sarpong and Morandi and Noah Barnes and so on, right? So they just basically, the idea is to take an oxygen out and put a nitrogen in. What is that affecting anyone? And I think that has potential for med chemists. And we started to look into it a little bit more later on. I mean, the PhD was working in something else. He was working in bismuth, so we kind of left this a little bit on the drawer, and we recovered it when a postdoc joined and saw this, and we started to make a little scope. And the cool thing is that you can do pyrazoles, but you can also do triazoles, right? And that is also cool. And we thought that med really cool. People would like it, and we just put together a small paper, and I think it's pretty nice, actually. I really like this reaction.
I love these little like synthetic letters, organic letter papers. They're like some of my favorites to read. It's like just so like here's this cool transformation, like, and it's like that's it. It's like, oh, that's really cool. But I kind of want to shift gears a little bit and talk about really your bismuth chemistry, because this is kind of really, I would say, taken off. What were some of the, like, I guess, starting up a new lab, you definitely, so, you definitely need you have some initial ideas. Was using bismuth to do organometallic reactions something you originally thought about, or how did this bismuth chemistry kind of begin to arise for your group?
So the original sort of in the very beginnings was obviously when I was a postdoc, right? Thinking on what would be cool to do in the future and so on. And I think the bismuth came pretty much from different, from different inputs that I had during my career. Lectures that I've been where people have said that bismuth is non-toxic. I remember Silas Cook from Indiana saying that in a conference and saying that it's abundant, and I didn't believe it, and then I went talk to him and it's like, really? And then he explained me, yes, blah blah. So to people that suggested that use all the elements of the periodic table because they are there for a reason, so sort of messages that kept sinking into my brain somehow, and yeah, eventually I decided to look into this into a bit more detail and into bismuth, and then I found all this old chemistry of Barton and Motherwell and that used bismuth in organic synthesis, like as an oxidant in bismuth 5, right, or arylating reagents. This is old chemistry that is very known, right? The stoichiometric high-valent bismuth chemistry is very, and it has been used in total synthesis, and people in Scripps, even when I was a postdoc, had used it, like Dale Boger and Phil Baran have used it. So coming from a transition metal mentality, I was like, all right, if you have a bismuth 5 and you deliver an aryl to some sort of nucleophile, and you get a bismuth 3, why not turning it back to bismuth 3, to bismuth 5 with an oxidant somehow, right? And make it catalytic. I mean, it's a waste of bismuth, it's a waste of aryl groups here with triphenyl bismuth. So that is a simple idea, right? But it's tricky. And I was reading a lot on high valent nickel and high valent palladium from Sam Ford and from Jing Kwan and from Tobias Ritter, right? And I was seeing these CH activations of palladium 2, palladium 4, so high valent catalytic cycles. And I was always puzzled and amazed by them. And I said, all right, maybe the bismuth 3,5 is also one of those. Who knows, right? Maybe we can do it. Well, that was one of the proposals, and also inspired a little bit by Radosevich, phosphorus 3, phosphorus 5 chemistry, right? Everything kind of, shake together. You put all these inputs, shake it, and my proposal sort of came up. And and then I went to the Max Planck, and here at the Max Planck, I presented this, and they liked it, and they bet on it. I guess they hired me. That was one of the proposals, But truly, like when we started here, we started getting, into the nickel catalysis at the very beginning to get momentum and to get a few articles out, because we knew that the bismuth would be like a long shot and something that we would really have to invest a lot of time to understand and to do, the proper organometallic steps to understand everything. So it was not until we had, I hired a postdoc that contacted me, Uri, that is now independent in the UK, in Queen Mary University, actually. So he's a prof there, and he joined my lab as a postdoc, as a Marie Curie Fellow, and he was really the one that pushed this chemistry, to realization. So we worked very hard for 2 years, and he came up with an enormous amount of ideas on how we can design the ligands and so on based on precedents and what we're going to do. And then eventually we made the low valent, right? We separated the low with the bismuth 1, bismuth 3, which was also a PhD student, Feng, that is, it was amazing. And he was basically also the pioneer that could have continued with the berylliums. And he said, no, I want to do bismuth chemistry, even though it's not working yet. So really, super brave guy and extremely skilled. So he stayed on the bismuth, and it was rewarding, I think. So he did the bismuth 1,3 with the help of Uri, this postdoc, and then Uri was much more focused on the 3,5, which eventually he pulled off. That's the beginning, right? And we started working, but we knew from the very beginning that it was not just a mix and a stir sort of chemistry. We needed to make complexes, isolate them, understand them, and once we understand them, probably we can do catalysis, and that is a little bit what happened.
Yeah, it seems like a lot of literally fundamental organometallic chemistry was coming out of here. It seems like
and we have these skills. He did a lot of organo-cobalt chemistry. He did a lot of organo-cobalt mainly in his PhD. And when he joined, he basically translated all those skills into the bismuth.
It seems like I was kind of like going through your publications. It seems like these tridentate imine ligands kind of scaffolds are kind of work some of the best for this bismuth chemistry. How did that, was it, maybe you did like a ton of ligand screenings to try and get these organometallic bismuth reagents, but
not really.
Why start there?
So this was also a very, Libor Dostal from the Czech Republic, a professor in the Czech Republic, reported these complexes in Angewandte Chemie in 2010, the first monomeric low-valent bismuth complexes. And it was this NCN sort of bis-imine pincer complexes. And when looking at this, Uri also looked at this and said, I'm going to prepare it. So he prepared it. And then I remember, let's try it in the transfer hydrogenation reaction of Radosevic. And the reaction worked. We were very lucky in that first hit. And then from then on, we started pulling from this. And we saw that this bismuth ones were incredible pre-catalyst. So we didn't move much from this scaffold in the low valent because there's so much juice still. That seminal report in 2010 was kind of a stepping stone for us. It was like, all right, from here, we take it from here and we are trying to understand this low valent chemistry. And it was super, it still is, giving us a lot of surprises and good stuff.
Yeah. Are these kind of bismuth complexes, they're stable? You have to kind of work in a glove box for these complexes.
Yeah, we work in a glove box. They are like this bismuth one has a lone pair that is very hot and it gets oxidized very easy.
Okay. Interesting. Yeah, I'm very, maybe you could also touch on, bismuth, as we said, bismuth is very, very abundant and also relatively non-toxic. So perhaps you could touch on that just a little bit for the viewers who are unfamiliar with bismuth, of why it's so advantageous, let's say, compared to, other organometallic or other transition metals, let's say.
So why bismuth is more advantageous than other transition metals?
I think it's definitely part of it for sure. Like, why you have a general sense of why, bismuth might be more advantageous than other transition metals. May or may not be. I don't know.
Yeah, that's the question, right? It might not be. So what we are trying to do is try to get the reactivity of it. First, understand what are the rules of engagement for bismuth, what is capable of doing. And what we have seen is that in some cases it mimics some chemistry of transition metals. Sometimes it mimics the chemistry of group 15 as it is a group 15 element. Sometimes behaves as a first row transition metal. Sometimes it behaves like a phosphorus. Sometimes it behaves like something different and new that we've never seen before, right? In sort of transition states that were inconceivable for transition metals. So it has a flavor of every element that we like, a little bit of a mix for the moment, and that is what it comes almost as a philosophical question of why so. Why is it behaving like a first row transition metal, also a little bit like a group 15, which is because it's a group 15, sometimes as a second row transition metal, more like a polar 2-3 sort of redox platform, or 3-5, sometimes a 1-2-3 single electron, sometimes just acts as a nucleophile, like if it was a hot phosphorus. So there is a lot of, and this is all in the same complex, right? And there is so much to study in just this scaffold that start to changing this scaffold would add even more variables to the system that we need to control first this one and then just get to the next level, right?
Yeah.
but there is so much to do and it's so rich. One of the peculiarities that can bring bismuth that we are exploring now is the relativistic effects. So we believe relativity plays a huge role in some of the reactivity that we see. Because it's gigantic, you have like these electron contractions and so on, and then the bonds are weak. And all this starts having consequences into the reactivity. And this is, I think, quite interesting because the effects of relativity to be exploited in organic synthesis, I think it sounds like something quite cool to investigate.
Right.
I mean, we have all this gold one catalysis that because of relativistic effects is also like biphilic and it brings triple bonds into the coordination sphere and so on, right? But all this redox chemistry affected by relativity, I kind of like the idea of looking into this a bit more.
Yeah. I'm excited to see what comes out. For the viewers, I know you recently published a perspective on bismuth chemistry, bismuth in organic and radical chemistry. So, that's out now. People are very interested in this bismuth chemistry. Go give that a read. That they'll pretty much summarize everything you need to know. I caught up the bismuth chemistry that's going on right now. So that's really exciting. The last kind of area of your research that I definitely want to talk on is on the beryllium salts to do really various transformations. What kind of inspired that work to begin with?
That work, it was inspired by reading the Portable Chemist book of Phil Baran. It's called Portable. I don't even know the type. Portable Chemist or something. Portable Chemist book, or I don't remember the name. Okay, so but this is this iPad sort of book of heterocyclic chemistry, right? I became a little bit obsessed with heterocyclic chemistry when I was at the Baran lab and learning a lot more because I didn't learn much of heterocyclic chemistry, how to make heterocycles, how to derivatize them. So I watched all these, field lectures, and then I get the book and I got into this book a lot. And I remember a transformation which was I don't even know if it's there anymore because they keep updating it, but there was a zinc salt, right, which is this when you take a pyridine. So it was the old synthesis of DMAP. So if you take pyridine with chlorodinitrobenzene and you hit it, what you get basically is the pyridinium chloride that crashes out. Okay, that is the zinc sort of precursor, the zinc salt. And if you take this zinc salt and you throw a dimethylamine. No, actually, no. This is another one. Oh man, I just got confused here. No, so if you take pyridine and you oxidatively dimerize it, you make a pyridinium pyridine. So it's a pyridine that attacks at the it's C4, right? So you make that adduct, which is a pyridine with another pyridinium on top. And if you throw now dimethylamine, what you get is DMAP. So I said, okay, that is cool. That is a cool reaction. It's formally an SNAR into a carbon pyridine bond, right? And then I said, if this pyridinium pyridine, we could make it from an amino pyridine and a pyrylium, basically all this reactivity is known, right? That came from just the simple dimerization of pyridine, which is useless and probably limited to pyridine only, right? So, but if we would like to apply amino heterocycles, right, we can take any amino heterocycle, condense it with a pyrylium. We would get to these intermediates, which are the pyridinium intermediates, that we know that can do SN2 or SNAR, with a pyridine. Well, that was the original idea. And then I had an extremely talented master's student that had a lot of experience in industry, Daniel, that prepared the pyrylium tetrafluoroborate, which was the salt that we needed to condense. And he succeeded, which was a challenging, actually very challenging synthesis. So it requires a skilled chemist to prepare that pyrylium tetrafluoroborate at the very beginning. Now we are more used. We made a few tweaks. We even prepared, reported an organic synthesis prep. If anyone wants to make it, it's commercially available. That's fine. But at the very beginning, it took us a long time, right? Because it polymerizes. It's very sensitive. It's a very electrophilic acyl, sort of synthon, right? At the 246 is very hot. So any nucleophile will go there, and we had to be very careful. but that's why. So amino groups target that beryllium, condenses, and then you get the pyridinium salts. And that was the beginning. It was very fun. And that had a lot of legs, as you can see. Like, we managed to do it with sulfonamides, we did it with amino tetracycles. We can put a carbon-oxygen bond. We can make carbochlorides. We can make carbon nitrogen, sulfones. It was pretty good.
I was saying, in like some of your most recent chemistry, you take the sulfonamides and make fluorine bonds. So how does that? Like how does that? Do you have a good sense of how that works? Like what's happening there?
No. But you take a sulfonamide and you make a sulfonyl fluoride.
Yeah, sulfonyl fluoride. Yeah.
Yeah, that's right. So you turn it into the sulfonyl chloride, and then in situ you have a fluoride-chloride exchange with potassium fluoride.
Okay.
So that idea came by reading the suffix chemistry of Barry Sharpless and so on. So all these people, right, that influenced us. And they said, okay, so sulfonyl fluorides seem pretty important. So if you take sulfonamides, you turn it into sulfonyl fluorides, that could be interesting. Yeah.
Yeah. So for these reactions, it's like kind of what is the role of the pyridinium salt then? Like, so what is that doing?
For the sulfonamide?
Yes, for that reaction.
So that condenses. So the NH2 condenses with the beryllium. We don't know if I don't think it fully wraps back and makes the pyridinium sulfonyl. I don't think so. But the magnesium chloride is chelating enough to turn that into a leaving group, and then the chloride is delivered and kicks out.
I gotcha.
That N pyridinium attached to it, right? Because we see pyridine as byproduct.
Yeah, actually,
should be the byproduct.
Really cool
we don't
chemistry.
Pyridine.
Right. Okay. That's really fascinating stuff. Well, as we kind of begin to wrap up here, Professor, I definitely want to ask you, what as prospective students, what can they kind of learn from the Cornella lab? Like, what kind of skills and can you get out of the chemistry in your lab?
So here, what we have is a group what we're trying to have is a group that mixes a little bit of expertises. So it's not just a hardcore organic synthesis lab. We have people that is trained in hardcore inorganic chemistry, people that are organic chemists by training, people that has been doing catalysis. And we are all kind of mixed in a setup where we learn from each other and everyone is bringing its own expertise. So it's not that, and we slowly build up a way of doing things. And what we like a lot is to go deep into into design of catalysis, right? That's what people usually come here to learn, is how we design catalytic systems and how we pick up interesting transformations that we can apply to, right? And for the bismuth especially, it requires much more rational design or understanding of the fundamentals of organometallic chemistry, right? And all this is basically the core, right? And we are surrounded and cushioned, I would say, and really helped by all the services and people that is here at the institute and the neighboring institute, right? So we have experts in every area. We have a great X-ray department, a great NMR department, a great SQUID, EPR, MCD, all these computational people that support and help us into our endeavors and make this a useful technologies.
Yep. Well, Professor Cornell, I want to thank you so much for coming on the podcast today. It's extremely awesome talking with you.
That's great. Yeah, it was a great podcast and a great time. Sorry, it's a great podcast and keep doing it. I really encourage you to keep doing this. It's great for us and for science and for everyone.
I appreciate it. Yeah, hopefully, bringing chemistry to the forefront is just a dream. Love this community, so we'll keep going. I'll make that a promise.
That should be the title of the podcast.
Alrighty. What title? Title what?
Bring it like the last thing you said, right?
Yeah. Okay. Yeah. I like it. Yeah.
You're kind of cut. I don't know. The whole interview has been cutting a little bit. I think my connection is not great, but I hope it's.
This is like halfway across the world. It's how it goes. Sorry, it's how it goes. So it's all right though. Well, Professor, thank you again so much, and
thanks.
We'll see you on see you guys the next one.